In the first video of this series, I will be focusing on acids and various definitions that have been proposed to classify a compound as an acid. In layman terms, we can call a substance as an acid if it tastes sour, or in laboratories we know them as substances that turn blue litmus red. But there are more precise definitions for acids. I will be covering them one by one. So first, let's see the definition given by Svante Arrhenius. According to him, acids are the substances that release H plus ions in solutions, or any substance that releases H plus ions in solution is an acid. So, in short, acids are the substances that release H plus ions. For example, I am considering a very commonly known acid, that is hydrochloric acid or HCl. And it dissociates in water or in aqueous solution to release H plus and Cl negative ions. So HCl can be called as an Arrhenius acid. As simple as that. Moving on to the Bronsted-Lowry definition, it says that acids are characterized by their ability to release protons, which in chemical equations is represented by H plus, or a hydrogen atom without an electron. So I can simply write it as acids are proton donors. Again, I will take a very common acid to illustrate this. I will consider aqueous H2SO4. In water, it will donate one of its H plus to produce H3O plus and bisulfate anion. So the reactants would be H3O plus and HSO4 negative, which is its conjugate base. So H2SO4 is a Bronsted acid. This is another simple definition and more general than Arrhenius or Arrhenius definition of acids. Let's come to the most precise definition given by Gilbert Lewis. He termed acids as molecules or ions capable of coordinating with unshared electron pairs, or the substances that readily accept those unshared electrons. So acids are electron acceptors. Similarly, Lewis bases are molecules or ions which have unshared electron pairs available for coordination. So let me write that. Lewis bases are electron donors. To understand this, let's first consider a Lewis acid, for example BF3 or boron trifluoride. In order to understand why BF3 acts as a Lewis acid, we have to look at its structure. Boron is the central atom with sp2 hybridization and trigonal planar geometry. So this is how the molecule looks. This is a planar structure, and it has one vacant p orbital which is of dumbbell shape, and half of the dumbbell is located above boron and half of the dumbbell is located below its plane. And this orbital can readily accept electrons to help boron complete its octet. That is the reason why BF3 can be called as a Lewis acid. One example of a Lewis base is trimethylamine. This is the molecular formula, and it has one lone pair which it can donate to Lewis acid. So if BF3 reacts with NMe3, the product will be a combination of both the molecules. So let's write it down. Boron trifluoride reacting with trimethylamine gives a coordination complex of both these compounds. These are attached by a shared electron pair. So this was all about the introduction. To measure the acidic strength of acids, first we have to quantify the strength. So I will now show how it's done. To measure the strength of an acid, we must quantify it and represent it on a scale. And to see how it's done, let's first write down the equation for dissociation of a typical acid HA and analyze it. So let me just write down the equation. This is HA, and in water, H2O. It dissociates as H3O plus and A negative, the conjugate base of HA. And the equilibrium constant Ka is simply given as Ka equal to concentration of H3O plus multiplied by concentration of A negative divided by concentration of HA. I have not included the concentration of water, H2O, in the expression for Ka. It is because water is assumed to be present in such excess that its concentration does not significantly change and is treated as constant, and that constant is incorporated into Ka. It can be concluded that Ka is the quantity that represents the strength of an acid. Higher the value of Ka, higher is the acidic strength, because that would mean H plus and A negative have been produced to a good extent. Let's say if we have three acids with dissociation constant of 10 to the power minus 5, 10 to the power 3, and 10 to the power minus 10. The second one is the strongest of all because it has the largest Ka value. There is another scale on which the strength can be measured in an easier way, and that is pKa, which stands for potential of Ka or potens of Ka or potential of Ka. It is given by formula negative logarithm of Ka with base 10. On this scale, the pKa values of these above mentioned acids would be 5, minus 3, and 10, which are simpler numbers to deal with. From this formula, we can see that pKa is low if Ka is high. or pKa is low if the acid is strong. That implies a low pKa corresponds to a strong acid and a high pKa corresponds to a weak acid. The formula also suggests that the acids for which Ka is less than 1 have a positive pKa value as their logarithm comes out to be negative. And this is the case with most organic acids. To summarize, we can write that a low pKa implies strong acid. I will now take an example on how to compare the strengths of two acids if their pKa values are given. So I will just assume the pKa values, evaluate their Ka values and determine their ratio. So let Ha1 and Ha2 be two hypothetical acids and their pKa values be 10. Let's say for Ha1 it is 10 and for Ha2 it is 12. So first we have to determine their respective Ka values, and to do that we have an equation governing the relationship between pKa and Ka. Hence for Ha1 we can write 10 equals minus log Ka1, base is 10, and Ka1 comes out to be 10 to the power minus 10. Similarly, we can do it for Ha2. Ka2 comes out to be 10 to the power minus 12. In this way, the ratio of Ka1 and Ka2 comes out to be 100. It is because it is 10 to the power minus 10 divided by 10 to the power minus 12, which amounts to 100. So Ha1 is 100 times stronger acid than Ha2 because its pKa is 2 units less than the latter. The pKa were 10 and 12. In general, the ratio of strength of any two acids Ha1 and Ha2 is given by let S Ha1 be strength of Ha1, and this comes out to be anti-log of or 10 to the power pKa2 minus pKa1. In the next section, we will study the factors governing the acidic strength of a molecule. Now to study the factors affecting the acidic strength of Ha, we will start with writing down the expression for dissociation constant again. And this is what I wrote a while ago. That means the factors that enhance the acidic strength will tend to increase the value of dissociation constant, that is Ka, and vice versa. So the first factor is strength of Ha bond, where A is the conjugate base. If the bond between H and A is weak, the acid will tend to break down easily and show more reactivity. And in this way, we will get a higher amount of H3O plus and A negative. For example, let's consider hydroiodic acid. The size difference between hydrogen and iodine atoms is very high. Let me show you. This is Hi, and the atoms of Hi, the atoms that comprise Hi molecule, look like H, and I. Since the size difference between hydrogen and iodine atoms is very high, the extent of overlap between these two atoms will obviously be poor, and Hi will easily dissociate into H plus and I minus, imparting the Ka a very high value. That implies Hi is a strong acid. Second factor, it is a set of all the factors that stabilize the conjugate base, A negative. If A negative is stable, more of it will be formed, and that means the concentration of A negative will be high, and that in turn will increase the value of Ka. For instance, we can take the formic acid molecule and examine its dissociation. The conjugate base is formate anion, and we will have to check if it is stable. So let's just write down the dissociation of formic acid. This is the structure of formate anion, and this is the proton released. The formate anion is stabilized by resonance. The second resonating structure is easy to draw, and we can see that these resonating structures are equivalent in nature, ensuring a symmetrical distribution of electrons, and this kind of resonance is extraordinarily effective in stabilizing the molecule. So formic acid is a very strong organic acid as compared to other classes of organic acid that are known. There is another factor that plays an important role, and that is nature of solvent. Let me just write that down. Scratch that. If the solvent is strongly basic, the acid will be keen to show its acidic properties. But if it has an appreciable acidic strength, then it will compete with Ha, or it will be reluctant to accept protons from it. So the acidic strength is high if the solvent is basic in nature, and low if the solvent is acidic. In the subsequent videos, I will be taking various examples of a variety of organic compounds on how to predict the acidic strength just by looking at their structures. If you found this tutorial to be helpful, please like, subscribe and share. And thanks for watching the video.